Thanks, Jonathan. Yeah, so my name's Connor. I build the Suborbital project, which is a group of open source tools and frameworks and runtimes that allow you to use WebAssembly and make it useful in server-side contexts. And so I'm going to talk today about specifically the Atmo project, because that is kind of the flagship. It's the main one. And I'll give a demo. I'll give a little bit of information about how it's built, the architecture, and some of the design patterns and reasoning behind it. And then hopefully there will be time for some questions at the end. So I will throw this up and we can get started. Hopefully I can maybe get a verification from Jonathan that he can see my screen.
I can see it.
All right, great. So yeah, let's jump right into it. So Suborbital, I kind of already touched on it, but it is, it is a collection of projects, but the overall goal of Suborbital is that server-side WebAssembly, endpoint, which is making it really easy to build, run, and actually develop applications for the server that are powered by WebAssembly. And it might be, a little bit weird to say this, but actually, I'm hoping that WebAssembly will become kind of an implementation detail. I'm hoping that, in a couple of years from now, WebAssembly is not going to be the headline feature, but rather just something under the hood, and it's going to become so commonplace that you won't even really care that WebAssembly is powering it. So the projects under the umbrella are kind of shown here. The three on the left, reactor, grav, and vector, are what I call the building blocks, and they are individual components that, when you put them together, form Atmo. So reactor is a job scheduler or a function scheduler, and this is actually where most of the WebAssembly magic happens. This is where we schedule WebAssembly modules, we manage their inputs and outputs, manage their memory, we load them and unload them from the disk, all sorts of things like that. And then grav is a decentralized message bus. So it is actually an abstraction over any kind of discovery and transport mechanisms that you might want to build your application on top of. It allows you to write asynchronous messaging and swap out transport and discovery plugins without needing to rewrite any of your code. And then vector is an HTTP framework for Go. Not exactly important when talking about WebAssembly, but it is kind of the first line of defense. It encodes a lot of security best practices and performance best practices to make sure that you are building a performant web server. And then, like I said, Atmo kind of puts all of this together. It allows you to run a scalable WebAssembly powered server-side system. It can scale, it can mesh together, communicate with a group of instances, and it kind of gives you the best of all these three while having a pretty unique development system. And Atmo has been developed alongside what I call the SUFA design pattern. And this is something that I've been working out to help me guide the actual development of Atmo itself and the development of the directive concept that I'll talk about in a minute. So SUFA stands for Simple Unified Function-Based Applications. And I think it's fairly straightforward, but I want to touch on each of those points in particular. So simple means that it is simple to both understand and simple to run. So, developing Atmo applications should be simple, and actually orchestrating and running and maintaining Atmo applications in a production environment should also be quite simple. You don't need a complex network topology. You don't need, all sorts of, services that your cloud provider gives and all the bells and whistles. Just an auto-scaling group is more than enough to run Atmo, and it shouldn't get more complicated than that. And then unified means that when you build your Atmo application, you are, it results in one singular thing. It is one deployable unit. It is one thing that needs to get deployed to the cloud or deployed to your environment. You don't have to build, dozens or hundreds of Docker images for all of your different microservices. It's meant to be entire project built into one unified deployable that Atmo then intelligently uses to build a scalable system in the cloud. And then function-based simply means that your application is comprised of, small, easy to build functions that are independent from one another and that basically take input, provide output, and we'll see how you fit those functions together to form an application in just a second. So I don't think I need to really answer this question for a WebAssembly meetup, but I think it's important to touch on, especially for, if you're new to WebAssembly or if you haven't seen it in a server-side context before. Why would we choose WebAssembly to build our server-side applications, and why did I choose WebAssembly to build Atmo and Suborbital on top of? And it comes down to these three things: portable, secure, and fast. WebAssembly is portable, meaning that it can run on all sorts of different processor architectures, any device types. You can run it on ARM, you can run it on x86, you can run it on the edge, central cloud, whatever you want. It is very flexible. It is secure because WebAssembly is based on a sandboxing model that is denied by default, meaning that, in order to grant code running inside of a WebAssembly sandbox access to things, it has to be explicitly granted to that module. You do not get anything necessarily for free. And that means that your code is very secure. And when you run that code, your environment is very secure, especially, for example, when executing third-party or untrusted code, you know that code can't do any hijinks because you have to explicitly grant it access to things. It can't just run rampant on your network or your file system. And then finally, it is fast. We've seen a lot of benchmarks lately. If you look in the Wasm Discord, or if you look on Twitter, there's been a fair amount of benchmarking happening lately, and it's pretty impressive. And there's been a fair amount of improvement. There are a bunch of different ways to build and compile and execute WebAssembly. There's ahead of time, there's just in time, there's all sorts of different strategies. But at the end of the day, what you're getting is something that is quite performant. And I think we're going to be seeing plenty more improvement in this area as we go forward. So the goal with Atmo is you write functions and compose them to form your business logic. And then you create what we call the directive. And then Atmo uses the directive to run your application and figure it out. It shouldn't be up to you, the developer, to dictate exactly how the application is run. Atmo is designed to be a little bit more intelligent and run the application in a way that it is best for the environment that it's in. And I'll talk a little bit about that at the very end. So this directive that I've been talking about, it is the way that you compose these functions together to form an application that can serve your business needs. And you do so with it's a declarative format called the directive. It's a YAML file, and it lets you describe everything about your application that Atmo would need to execute it properly. So you can see things like, API endpoints are being defined, and a set of steps are given to, handle requests to that API endpoint. And so you can see, the ability to call functions, the ability to have iterators that allow you to do lots of really great, loops and conditionals, and, the ability to run concurrent jobs, and the ability to do things like, set environments specifically for each function. And there's a bunch of other powers that this has, like error handling, and I'll kind of get into that a little bit later in the demo. But the main takeaway and the main reason why Atmo is designed around this declarative format is that it allows you as the developer to care about what is being run, and you let Atmo figure out how to run it. And this will get more useful as Atmo and the suborbital ecosystem evolves to span different computing environments like central cloud and edge cloud, because Atmo will be able to intelligently decide where particular functions within your application should run, and determine, should something run on the edge, should something run in the central cloud. And because you've designed your application with a declarative format, you don't need to rewrite anything. You don't even need to know which functions are running where. As long as Atmo executes your steps as described, let Atmo decide what is the most efficient way to run your code. So I'll do a quick peek into Atmos architecture internally. I mentioned before that reactor, grav, and vector are the building blocks, and they truly are building blocks towards creating Atmo, because all three of them are well represented within Atmos internals. So it all starts when network requests come into an Atmos server. They are handled by an instance of the vector server, what we call VK. And VK does all of the handling of TLS. It does all the routing, and it does all sorts of logging and ensuring that your application is being handled with the best performance possible. And it hands individual requests off to what's called the Atmo Coordinator. And the coordinator is kind of the brains of Atmo. It's the glue that kind of sticks these three building blocks together. And it is the thing that is reading your directive and instructing the system as a whole to execute the functions of your application in the right order, and handle the what should be input into certain functions and what to do with the outputs of those functions. And it does that by communicating over the grav mesh, or the grav bus. And it's important to note that because grav is the intermediary for all function calls within Atmo, it means that the function being called by the coordinator doesn't necessarily have to be right on the actual instance of Atmo where the request is received. Because grav can be networked and can mesh together many instances, the function being called might actually be on a different box, or might be in a different VPC even. And so by executing function calls over this message bus, it allows us to be intelligent and distribute these functions across many instances if needed. And Atmo can intelligently load and unload functions from its internal scheduler to make room or to be more efficient when needed. And all of that execution is done within an instance of the reactor scheduler. So whether the message to execute a function is coming from internally within the instance itself, or coming over the network from another instance, that message is received by reactor, and reactor will actually run the WebAssembly module associated with the function, and it will ensure that the correct input is given, and it will then send the output back as a response message, which will then be received by the Atmo coordinator that originated the request. And so this gives us a really flexible platform to build applications on top of, and it especially shows why the declarative nature of the directive is important, because it allows Atmo to make those decisions of, do I mesh to a different instance that has the function already loaded, or do I try to load that function myself and put it into memory and execute it myself? Atmo can kind of do those decisions as needed. So I think that's enough talking. I'm going to give you a bit of a demo. So I've got an application here called Telescope. It's actually open source. So if you head over to my GitHub, Hicks, and you can find the Telescope repo if you want to follow along. And it all centers around that directive file. So that's always going to be the entry point for an Atmo application. It includes a little bit of metadata, like what version of Atmo are we using, for example. And then it describes all of the handlers of the application. So there's a couple of different ones here, and I'll go into some of them in more detail. But at a high level, we have an endpoint for getting some files. We have an endpoint for listing some repos. We have endpoint for getting a particular repo, and then we have this one at the bottom, which is for creating a report. And I'm going to talk about this one a little bit later. But we'll start with this list repos endpoint, because it's fairly straightforward, and I want to walk through how the directive interacts with the various functions in your application. So you can see that we're handling something that looks like a request, and it's coming to this endpoint, and it's got this HTTP method. Okay, fair enough. That's pretty straightforward. And then in the steps to handle this endpoint, we are calling a function, and this function is called list repos. So let's go check that out. This one is written in Rust. but Atmo and the suborbital projects do support multiple languages. You can use Rust, you can use Swift, and assembly script is coming like within days. I have most of that completed, and assembly script will be up in public probably with Atmo Beta 3, which will be coming pretty soon. So each of these, things in the project are functions, and they encapsulate a particular piece of business logic. So the list repos function in particular, it's designed to fetch a list of the repositories within a particular GitHub organization. And in order to do that, we actually can use what is called the Suborbital Runnable API, which is a set of capabilities that have been granted to the functions in an Atmo application by means of this runnable library. So there's a library for each of the supported languages that gives you access to these capabilities. So I'm going to talk about a bunch of these, but just as you can see here, like these are some of the things that are available to you: accessing a cache, reading files, making HTTP requests, and more. So we're going to use that right off the bat, and we're going to use this file capability to get a static file. And that's actually one of the features of Atmo, is the ability to bundle static files with your application. And so when I build the Atmo application, that unified deployable that I talked about earlier, the form that it takes for Atmo is what's called a runnable bundle. And this is a zip file that contains everything Atmo needs to run your application. You can see it here in the project. It gets built along with everything else. And so, all of the WebAssembly modules that get compiled from your functions, all of your static files that you want to bundle, and your directives all get put into this runnable bundle, which Atmo then reads to actually run your application. So we use that get static function from the file capability to read this organization file, which tells us which GitHub org it is we're dealing with here. And then it uses the HTTP capability to make a request to the GitHub API to then actually get information about the repos in the organization in question. And then we do some JSON work, nothing fancy. And then what we're actually going to do is, for each of those repositories that we get back, we're actually going to cache them. So we're going to use Atmos cache capability to store details of these repos for use later. And we can do things like set TTL. And this cache is something that's configurable. So when you're running a dev server, it'll be an in-memory cache, but you can connect it to things like Redis or whatever you want to do. So then we respond with JSON, and call it a day. We can do things like setting content type and headers and all that fun HTTP stuff. So let's we'll take a pause, and we'll actually build this thing and give it a try. So Suborbital has a CLI tool. It's called Subo. And if I run subo build, I'm going to pass dot for the current repository. And I'm actually going to pass a flag called native that instructs Subo to use my machine's native toolchains. So the actual Rust, Cargo, and Swift compilers that are installed on my machine. By default, Subo actually ships with a Docker-based toolchain. So you don't actually need to install any of the toolchains or any of the CLIs and the various Rust targets and all the different things to build WebAssembly. Subo will actually do that for you. As long as you have Docker installed, it will kind of figure out how to do that for you. So as soon as I hit that, it's going to compile each of the functions in my project. It's going to add all the static files to my bundle. I'm going to make this font a little bit bigger just in case. It's going to add all of those static files to the output bundle. And then this zip will contain everything that Atmo needs. And I'm going to start up an Atmo dev server by running sudo dev. And this is going to actually read that bundle and create my application. So Atmo starts up and it serves on 8080. So why don't we go and pop open an HTTP client, and we can take a look. Postman always takes a second. Here it is. Okay. So we will start by calling that repos endpoint. You'll remember that that was defined here in the directive with the get method. So if I make a call to that, we will get a response with all of the different repositories from the suborbital organization, which is really cool. Now, you remembered me say that we cache the details of each of these repos, and I want to show that that's actually working. So you'll see here, it took about a little under 300 milliseconds to get this all back. We were doing a network hop to the GitHub API, had to do TLS, all that kind of stuff. So yeah, it's not the fastest. But if I go over here and I actually make a request for a specific repo, if I ask for just the Atmo details of the Atmo repo, you'll see that I get that response back in just a couple of milliseconds because Atmo is actually reading that from the cache. So why don't we go take a look and see what that's all about. So if we go to the get repo function, this one is for, like I said, getting a particular repo. And it's doing some similar things. It's reading that file, the configuration file, to determine what organization it's mapped to, and then it's actually checking the cache right off the bat to see if the repo details are stored there. And if they're not, then it'll go to the GitHub API and it will fetch that repo, fresh, and then fill the cache back in behind it because it's a good citizen. But if it did actually find it, then cool, we have the JSON for that repo, so we'll just return it, no big deal. So this is a pretty good representation of how to use the runnable API and gain access to things you would commonly need to build a web service. But let's maybe get a little bit more complicated. So let's take a look at this report API here. So this endpoint actually has multiple steps involved and has a little bit of extra configuration. So first off, the point of this endpoint is to create a report of the stars on the repos in the organization that we're configured to connect to. And so, this is a post endpoint. We're going to hit the API v1 report endpoint, and we're going to execute a couple of different runnables or functions to handle this. So the first one is that list repos function that we saw up above. So you can kind of see that you can reuse functions among different endpoints and get some nice modularity there. And we're using a clause here called as, and I'll take a second to explain how the functions within a handler actually interact with each other. So when you're executing the steps to handle a request, Atmo is creating what's called the request state object. This is an ephemeral object that exists just for the lifetime of the request. And for each function that executes, its output gets stored into this state object. And it's essentially a dictionary, like a map of key value pairs. And so the list repos output gets stored into that object so that functions later down in the chain can actually access the information that was returned. And list repos is a weird name to be accessing information from. So you can actually alias the value in the state object by using the as clause. So it's basically essentially run list repos and store it as repos in the state. And so that brings us to the second step in this handler, which is a for each operator. And for each allows you to iterate over an array and execute a function on each element of that array. So you can see here, we're actually going to take the JSON array that we got back from the list repos endpoint, which is an array of repositories, and we are going to execute the send report function on each element of that array. And we'll see how that works in just a second. So why don't we take a look at that send report function here? So, somewhat similarly, we're using the runnable API to gain access to some capabilities. But this one's a little bit different because we are using the request capability to actually access that state that I talked about a second ago. And we're accessing a special key called LM, which is what gets set when using an iterator. So when the send report function is executed, it's being executed on one element of the array stored in the repos value. And in order to get the value of that element, we ask Atmo, please give me the LM that I am being executed on. And so we do some similar things here. We do, the JSON dance to unmarshal that into a repo object. And we're going to filter out repos with less than 5 stars because, no need to create a report about those. And then we are going to use that same file capability with the get static to fetch a different configuration file here called webhook that I'm not going to show you because I don't want you to spam my Discord channel, but it's going to read a Discord webhook URL from that file and then build a webhook payload and send that webhook to Discord. So you can see you can do all sorts of things like setting headers on those requests and setting the body and all sorts of standard stuff that you would expect from an HTTP client. So to summarize, we're going to get a list of the repos in the suborbital organization, and then for each of the repos in that list, we're going to send a report only if there's more than 5 stars. So we'll give that a try. I've got the configured Discord channel here. It's called reports within the suborbital Discord. If you want to join, just go to chat.discord.dev and that'll bring you right to the Discord channel. So let's hit that report endpoint, the API v1 report with a post request, and we'll see what happens. So I'll quickly go over here and show you that the output of the Atmo instance is running here, and it's showing you stuff like API v1 report completed with 200, etc. And we can see that the response of this post request was the same as the list repos because we're just passing that along to the caller. But then we pop back over to this Discord channel and we can see that we got information about the repos under suborbital with more than 5 stars, which is pretty neat. So this is all great. We built an API. That API has some pretty cool endpoints, and we can build and reuse functions, compose those functions together to form the business logic of our application. But I do have one more little tidbit to go on the end of this. I'm going to kill this Atmo server for just a second, and I'm going to run a different build command. And I'm not going to spoil it, but Telescope is actually a full stack WebAssembly app. And well, what does that mean? So I've just built an extra component to this application, and I'm going to restart that dev server just so that we can maybe give it a try. And if you look at the Telescope repo, it directs you to this particular URL. So why don't we hit that? Okay, well, we're getting a web version of the information about the repos in the suborbital organization. So this is kind of cool, but what's special about it? Well, the answer is that this is actually a front-end application built using WebAssembly. So if you look here, the application is built in Rust, and it uses the U framework to actually manipulate the DOM and build a single page application. So if you look inside of this app directory within the static part of the application, you can see that the make command that I ran took that U application and built it into an HTML page with some CSS and a WebAssembly module that is being served by Atmo from this static bundle to the browser. And then the front end compiled to WebAssembly is interacting with the backend compiled to WebAssembly. So essentially, this is a full stack WebAssembly application where the front end and the back end are both entirely built using WebAssembly. I'll give you a very quick tour of the web app, and then we will call it a day. So we'll take a look first at the main.rs. So this is kind of like the index of the application. We're setting up a component. The component is called homepage. It has various lifecycle methods like create and rendered and updated, and etc. And then a view method, which actually does rendering of some HTML. So we are creating various elements, and then we are using the U framework's APIs to actually iterate over some Rust structs to create the list. And the information is being fetched from this API function called getRepos, and this is actually making a fetch request, like a browser API fetch request, to that backend service. And then the result is being put into this model repo struct that you can see here. And if you take a look, model is actually living over here on its own. It's the repo struct is not specific to the front end to the back end. And if we look at the list repos function once again, we will actually see that when we are unmarshalling the JSON that we get back from the GitHub API, we're using that exact same model repo struct. So we're actually sharing code between the front end and back end, compiling them both to WebAssembly, and then running them both in the browser and on the back end using U on the front end and Atmo on the back end. So that's the whole entirety of what I have to show. I'll switch back over the slides real quick and just say thank you. That's the end of what I want to show. You can head over to suborbital.dev to get all the information about Suborbital's projects and visit the GitHub repo as well. Give Atmo a look, try it out, clone it, run the Subo CLI tool, give all the feedback that you can. And you can follow me at Hicks on Twitter, and Suborbital is Suborbital Dev on Twitter as well. So that's it for me. Let's maybe see if there's any questions.